In technical terms, entropy refers to the distribution of available energy among particles. However, we tend to simplify things a little bit in IB chemistry, so when talking about entropy, we're really considering how we might measure the disorder in a system. To try and demonstrate what we mean by disorder, let's first of all look at an example of a small lump of solid in a box. You'll notice in the box that I've drawn some grey grid lines to represent the possible places where particles could be. However, as we know about solids, my particles are in a fixed position. And if I consider the different possible arrangements in this solid, the particles have to be in these four boxes next to each other, because solids do not fill the shape of the container. So I could switch positions, maybe the yellow and the purple one would switch, or the red and the blue could be switched. But in total, there are only a few possible arrangements of those four particles within that grey box. Therefore, we have a relatively low energy distribution that's possible. And this means that we would consider this a low entropy system. Let's now compare a solid to a gas. We should know that gas particles can move around freely in their container. So I could find many possible arrangements where my four coloured particles could be in any of those grey boxes in a number of different ways. So in comparison to my solid, I have a high energy distribution that's possible, and therefore this would be considered a higher entropy state. And let's consider a third system where I simply add some more particles to my gas. Now, because I have even more particles, there are even more possible arrangements of those particles in the grey boxes, meaning I have an even higher energy distribution possible. So this is an even higher entropy state than the first gas. Again, we can think about this mathematically, but in IB chemistry, if we can understand the concept of disorder, then it's a little easier to work with. So, why do we care about entropy? Well, it's important because it helps predict the direction of change in a chemical process. And this is because, according to the second law of thermodynamics, a spontaneous change will increase entropy in the universe. And what do we mean by a spontaneous change? Well, all we mean is that it's going to occur without us needing to do any work. Let's take a simple example of a bottle of Coke. You might know that the fizziness in Coke and, well, most fizzy drinks is caused by dissolved carbon dioxide in the liquid. Because those carbon dioxide molecules have been forced into the liquid, there's a fairly low energy distribution of those particles. Therefore, this would be considered a relatively low entropy state. And as you know, if you open the lid of your Coke bottle, without doing anything at all, you will start to see bubbles forming and those carbon dioxide molecules leaving as a gas. So why does this process happen spontaneously? Well, those carbon dioxide molecules that had been forced into the solution, into a low entropy state, are now escaping into a gaseous state, which has a much greater degree of disorder. So as those carbon dioxide molecules are escaping, we are increasing entropy in the universe. Let's perhaps look at an example of a chemical reaction. Well, it's going to be the same thing as we saw previously, except with a chemical reaction, there will always be an activation energy required to start the chemical reaction. So if I take the example of a candle, once I've used a small amount of energy from my match to light the candle, and the activation energy has been overcome, we will find that my candle will remain lit and keep reacting until the candle's gone. So if it continues without us needing to do any further work, it must be increasing the entropy in the universe. And in this case, it's because the heat released from this chemical reaction is increasing the speed of air particles around it, leading to a higher degree of disorder and therefore increasing entropy in the universe. Let's now consider the key points from this video. Entropy, with the symbol S, refers to the distribution of available energy among particles. Put more simply, it's a measurement of disorder in a system. And this is important because through the second law of thermodynamics, we know that a spontaneous change will increase the entropy in the universe. So in order to predict whether something will be spontaneous or not, we might consider three things. Firstly, we could consider the state of matter. Secondly, we might consider the number of particles in the system. And thirdly, we might consider how energy changes during the reaction will affect disorder. And that's it for entropy. Hopefully, this video is of some help.